So now let's start discussing about acoustics. What is acoustics? Okay, acoustics is defined as a branch of physics which deals with the study of sound, its generation, and transmission. In this branch of physics, we are going to understand the different properties of sound, behavior of sound, and sound propagation. Now you can see here an animation of sound wave. So you have here a tuning fork producing a sound, and you can see there is compression and rarefaction. I already have discussed this when we introduced the nature of waves. When you can see here higher density, so the air is more compressed, so that is what we call compression. And then dun naman sa mga lower density, or it's not very compressed, the air is not that compressed, so that is rarefaction. So there's lower pressure in the rarefaction and then higher pressure in the compression. Is sound wave a longitudinal wave or a transverse wave? So again, sound wave is a longitudinal wave, wherein the movement of the particles are parallel with the movement or the propagation of the energy of sound. Okay, so you can see there, yung red, yun yung compression, and then yung blue lines, they are the rarefactions. Okay. Now, is sound wave a mechanical wave? Now, from the previous discussion also, we had an animation or we had a simulation about sound being a mechanical wave. So mechanical wave needs a medium to transport energy from one location to another. If there is no particle, if there is no air particles, we cannot hear the sound. So in empty space, we cannot transmit sound. Okay, so again, it needs a medium for it to travel. So this was a demonstration when we discussed the nature of waves. So make sure that you have to watch the video on the nature of waves. Sound depends on the particle interaction for it to transfer energy from one point to another. Now we will be discussing the different properties of sound. Some of the properties are frequency, amplitude, speed, and then timbre. So when we say frequency, just like in our discussion, this tells us about the number of waves passing through a certain point at a particular time. Or it's also known as the number of vibrations per unit time. It is also a reciprocal of period. Okay, for the amplitude, this tells us about the height of the wave. It is also the amount of energy that the wave carries. Then we have the speed of sound. It is also V equals lambda F, where V is the velocity of sound, lambda is the wavelength, and then F is the frequency. And then the velocity of sound is also temperature dependent. You have here the velocity equals 331.5 meters per second plus 0.6 temperature in degrees Celsius. So that's how speed of sound is affected by temperature. So you can see here we have different speeds of sound for various media. For air, it's 343. For air at 0 degrees Celsius is 331. So for helium, it's 1005 meters per second. You can see here, iron and steel, it's approximately 5000 meters per second. Hardwood, approximately 4000 meters per second. So this sound travels faster in solids. Bakit kaya? Okay, as we all know, solids are very compact. So the particle-to-particle distance is very small. That's why it's easier to transfer sound energy from particle to particle. Okay, unlike in water and in air. Okay, again, we have here the speed of sound as affected by the temperature, 331.5 meters per second plus 0.6 times temperature in degrees Celsius. Okay, now I want you to look at this animation and also listen to the sound. Okay, so we have here, we are producing sound with a frequency of 535 Hz. I want you to observe what will happen to the sound as I vary or as I change the frequency. I'm trying to lower the frequency. Then try to increase it again. There. Now, what is the factor affected by that frequency? As I increase the frequency, what do you observe? As the frequency is decreased, what do you observe also? Okay. Now next, how about the amplitude? Okay, this one again. Then what I will do is decrease the amplitude. And then increase it. So what happened to the sound as the amplitude is increased or is decreased? Okay. Okay, so you can see from the animation or from the simulation what was affected by the frequency. Let's take a look at this. Pitch is defined as the highness or lowness of a sound. If you will compare this illustration, it has low pitch, and then this illustration has higher pitch. So which do you think has higher frequency? From the illustration, yung higher pitch has higher frequency. Therefore, the frequency is the one affecting the pitch of the sound. Pitch is directly proportional to the frequency of the waves. The higher the frequency of the waves, the higher is the pitch of the sound. Okay, we also have this what we call ultrasonic sound. Sound waves above 20,000 hertz. And then we also have this infrasonic sound. Sound waves below 20 hertz and below the audible range. Okay? So, ang audible range natin is in between 20 hertz to 20,000 hertz. You have here, in the other part of the animation, we changed the amplitudes. And then it resulted to difference in the intensities of the sound. Kapag soft sound, okay, we have here the waves, and then louder sound, what do you observe? What's the difference? Okay, the difference would be the height of the wave, which is the amplitude. Then from this, we can also relate that the intensity of sound is directly proportional to the amplitude of sound. So we will describe also loudness of sound by means of pressure and sound pressure levels. So you have here different kinds of sounds, and then their different sound pressure level. How loud is too loud? So yun yung mga intensities. We have in decibels, we have 40, 60. A normal conversation would be within 60. And then if you have an iPad at peak volumes, it will be 115 decibels already. Okay, take note that the safe exposure limit is 85 decibels for 8 hours a day. So you can check if what you are listening to is still within the safe exposure limit. Yan yung different intensities of sound. Intensity of sound is defined as the energy transported by a wave per unit time across unit area. So it's measured in watts. So that's it's a unit for power, watts per meter squared. Okay? Then sound intensity levels is expressed using logarithmic scale. The unit of intensity of sound is Bell, named after Alexander Graham Bell. So this is our intensity of sound in decibel. So 10 decibels is equivalent to 1 bell. So yan, 10 logarithmic I over I naught. So how are we going to interpret this one? For example, here we have different intensity levels in decibels. We have ordinary conversation 65, busy street traffic 70, siren at 30 meters 100, and so on. Then you have here threshold of hearing, we have 0. And then the rustle of leaves, we have 10. Whisper is 20. Quiet radio is 40. So how do we interpret this? Okay, this is how we interpret this. For example, threshold of hearing is 0, then rustle of leaves is 10. That means rustle of leaves would have 10 times the intensity of threshold of hearing. While if we have whisper, compared it to threshold of hearing, whisper will have 100 times the intensity than the threshold of hearing. Okay, next property is timbre, which refers to the quality of sound. Timbre is the quality of sound. So you can see here that different instruments produce different sounds or different quality of sounds because of timbre. Now it depends on the waveforms produced by such instrument. The same with human voice. We may be able to sing same song, but we sound differently because of timbre. We have different qualities of sound. Let's take a look at this example.
And now I'm all alone again, nowhere to turn, no one to go to. Without a home, without a friend, without a face to say hello to. But now the night is near, now I can make believe he's here. Sometimes I walk alone at night when everybody else is sleeping. I think of him and then I'm happy with the company I'm keeping. The city goes to bed and I can live inside my head. On my own, pretending he's beside me. All alone, I walk with him till morning. Without him, I feel his arms around me. And when I lose my way, I close my eyes and he has found me. On my own, pretending he's beside me. All alone, I walk with him till morning. Without him, I feel his arms around me. And when I lose my way, I close my eyes, and he has found me. In the rain, the pavement shines like silver. All the lights are misty in the river. Without me, his world will go on turning, a world that's full of happiness that I have never known.
Ay, lesson vlog pala ito. Okay, so let's now solve problems about sound. Okay, so you have here calculate the wavelengths in air at 20 degrees Celsius for sounds in the maximum range of human hearing, 20 Hz to 20,000 Hz. Okay, we have velocity equals 331.5 meters per second plus 0.6 temperature. Temperature should be in degrees Celsius, meters per second. Okay, so just copy that 331.5 plus 0.6, then substitute temperature 20 degrees Celsius. Then you will have the velocity. The velocity is equal to 343.5 meters per second. But we have to look for the wavelength. So V equals lambda F. We have wavelength times frequency. So looking for the wavelength, let's derive an equation. It will be wavelength equals V over F. Okay, let's solve. So lambda is equal to 343.5 meters per second divided by the frequency, which is 20 Hz or 21 per second. So our wavelength is wavelength is 17.18 meters. Okay, lambda is equal to 343.5 meters per second divided by 20,000 Hertz. Okay, the answer is we have 0.017 meters. So as you can see here, the higher the frequency is, the lower is the wavelength. Okay, so we have the wavelength for 20 Hz, 17.18 meters. But for 20,000 Hz, we have 0.017 meters. Next, what is the speed of sound at the normal boiling temperature of water? So the normal boiling temperature of water is 100 degrees Celsius. Okay, velocity is 331.5 meters per second plus 0.6. Then temperature is 100 meters per second. Our answer is 391.5 meters per second. Next, if the speed of sound in seawater is 1,560 meters per second, what is the wavelength of a 100 kilohertz sound made by a dolphin? What is the wavelength of a 100 kilohertz sound made by a bat in air at 20 degrees Celsius? Okay, velocity is 1,560 meters per second. Okay, velocity is 1,560 meters per second. And V equals lambda F. We are looking for the wavelength. So divide both sides by frequency. We have wavelength equals V over F. If 1,560 meters per second divided by 100 kilohertz, so that will be 100,000 hertz. So our answer is okay, we now have okay, our answer is 0.016 meters. Okay, next is what is the wavelength of a 100 kilohertz sound made by a bat in air at 20 degrees Celsius? So we have velocity equals 331.5 plus 0.6 times 20. Okay, we have velocity is 343.5 meters per second. Then to solve for the lambda, we have V over F. Okay, 343.5 divided by 100 kilohertz, so that is also 100,000 hertz. Okay, our answer is 0.003 meters. Okay, next, what is the frequency of ultrasound with a wavelength of 0.25 millimeters in tissue if the speed of sound is 1,500 meters per second? So velocity equals lambda f. Then frequency equals velocity over lambda. So that is 1,500 meters per second divided by, and 0.25 millimeters is 0.25 times 10 to negative 3 meters. Okay. So 0.25 times 10 to the negative 3. The answer is okay, we have 6 million hertz. So that would be the end of our discussion. Thank you for learning. So see you again.